So we've now described some key steps in constructing a log linear tagger. Firstly, how to define features that take into account features of the context or the history in conjunction with the current tag being predicted. Secondly, we've described how to estimate the parameters of this model, essentially by optimizing regularized log likelihood in exactly the same way we saw in last week's lectures on log linear models. The final piece of the puzzle is the question of how we apply a log linear model to a new test sentence. So this means we're going to take some test sentences input, for example, the dog barks, and we're going to search over all possible tag sequences for the tag sequence that maximizes this conditional probability. So we might consider the tag sequence DDD, DDN, DND, and so on and so on. And we're going to return the tag sequence that has the highest value for this conditional probability. Now, as usual, and as argued earlier in this course, brute force search just isn't going to scale to any appreciable sentence length. There's no way I can explicitly enumerate all possible tag sequences, calculate the probability of each such sequence, and then return the highest one. But we'll see that we can again use the Viterbi algorithm. And actually it's a very minor variant of the Viterbi algorithm as seen for hidden Markov models, and that will find the highest scoring or the highest probability tag sequence very efficiently. And the critical observation is that we're going to make the assumption that this conditional probability takes the following form. So notice I have a product from I equals 1 to n, and I have q of ti, given the previous two tags, the entire sentence, and the position. The key property of this definition is that at each point I condition just on the previous two tags. I have this Markov-like assumption, and that will again allow us to apply dynamic programming, or the Viterbi algorithm, to this problem of finding the highest scoring tag sequence. As it happens in our case, this Q, this estimate, is the output from our log linear model, which makes direct use of parameters and these features that we saw earlier. So let's build up the Viterbi algorithm in this case in a very similar way to the way we saw for hidden Markov models. So a key idea will be to define a dynamic programming table. So pi kuv is going to be the maximum probability of any tag sequence ending in tags u and v at position k. So a little bit more formally, we'll define a function r, which takes a sequence of k tags, t1 through tk, and calculates their probability under the model. So notice this is basically a truncated form of the probability for an entire tag sequence. We're now multiplying through I equals 1 to k, q of ti, given the previous two tags. And we define pi kuv to simply be the maximum probability for any tag sequence ending in u and v at positions k. So that's what this definition is saying. Again, that's very similar to what we saw for hidden Markov models. In hidden Markov models, we also saw a dynamic programming table of this form, where these pi values correspond to maximum probabilities of prefixes of tag sequences. Here's the recursive definition. So firstly, we say that pi of 0 at star star equals 1. That's the base case of the recursion. This is identical to the HMM algorithm. So no changes there. And then our recursive definition looks like the following. So again, we'll define S sub k to be the set of possible tags at position k in the sentence. That's exactly the same as the definition for the algorithm for hidden Markov models. And then for any k, for any u in sk minus 1 and v in sk, I define pi kuv to be the following. I take the max over all tags at position k minus 2. I multiply in pi of k minus 1 of tu. So that's a pi value at position k minus 1. Note we have position k over here. And then here I just have the conditional probability of v given the previous two tags t and u, given the entire sentence w, and given the position k. And so this would be the output from a log linear model. Now I'm not going to go through the justification for this recursion in great detail, but it is extremely similar to the justification we saw for the recursion when applied to hidden Markov models. So in fact, what's happened here essentially is that in hidden Markov models, instead of this term, we would have had something like the following. We would have had q of v given tu, and then secondly e of wk, because we have the kth word, given tag v. So we'd have this product of two terms, the trigram term for a tag, and then the emission term for the probability of wk being emitted by v. In this log linear model, we have this new term, which is the conditional probability of v given t and u, under the entire sentence w1 through n and the position k. Otherwise, this recursive definition is almost exactly the same as what we saw before. So here is the Viterbi algorithm which puts all of these ideas together. And again, I want to stress it's very similar to the Viterbi algorithm you saw for hidden Markov models. So the input to the algorithm is a test sentence, w1 through wn, which we'd like to tag. And in addition, we'll assume that we're provided with a log linear model that provides the conditional probability of any v given tags t and u, given an input sentence and a position. So those are the two inputs to the model. The model then proceeds as follows. So in the initialization step, we set pi 0 star star equal to 1. And then we do the following. So for every position k in the range 1 to n, we consider all possible tags, u at position k minus 1 and v at position k. And we're going to fill in the value for pi k of u and v. We do that by searching for the tag t at position k minus 2 that maximizes the product of these two terms. So I have pi of k minus 1 t and u, and then I have this q term reflecting the conditional probability of the tag v in this particular context, under this particular history. As before, I keep track of back pointers for every k, u, v triple, which just record the argmax, that is the tag t, that actually achieves this maximum. So that's the main body of the algorithm. Once I've completed these steps, I can then find the highest scoring tag sequence by following the back pointers backwards through the sequence. So I firstly set tn-1 and tn to be the uv pair that maximizes pi n, u, and v. And then I work backwards through the sequence from position n-2 down to 1, at each point saying the kth tag is equal to the back pointer for position k plus 2 with tk plus 1 and tk plus 2. So I'm essentially working backwards through the sequence, first recovering the last two tags, say d of n, d and then n, and then filling in the previous tags one by one backwards through the sequence. Once I've done that, I finally return the tag sequence t1 through tn, and that is the highest probability sequence under the log linear model.